So let's talk about uniform circular motion. That's motion in a circle at a constant speed. So we can think of this thing as an object like a car that's traveling around a circular track. So I can draw the car maybe at two positions here and say, I don't know, here, right? And this is a car going around a circular track. Or it could be a planet in orbit around a star. You know, here's the center of my circle, or it could be a ball being pulled on a string or something like that. The point is the object's moving in a circle at a constant speed. And so my first question to you is if we call this time t1, if we call this just position 1, say, and over here this is position 2, then I can say is v1 equal to v2. In other words, this is velocity at this position equal to the velocity at that position, given that the speed is constant. And so you can pause this and think about that for a minute. But I'm going to go ahead and tell you the answer. This is the direction of the velocity at this point. This is v1, right? And again, velocity is magnitude and direction. And so over here is the velocity v2. This is its velocity at time 2, t2 at position 2. And you can see that the velocities are not the same, right? They're not the same because their directions are different, even though the speeds are the same. So what we could say is equal is we could say the magnitude of v1, right, is equal to the magnitude of v2, but their directions are not the same. And so that means this object is accelerating, right? And so the acceleration, we can say, is not equal to 0. And so we can ask the question, well, what is the acceleration? That's kind of what we're trying to find out here. And so what I want to do here is I'm going to redraw v1 and v2, but I'm going to draw them from the same point. So I'm going to say, here's v1, here's v1, and I'm going to try to draw v1 from v2 from right here as well. I just tried to redraw v2 this way. And if we're going to say that v2 minus v1 is equal to delta v, right? Or we could say v2 is equal to v1 plus delta v, right? Then delta v must be this, right? That's what our delta v has to be, so that when we add v1 to delta v, we get v2, right? You could go back to our old way of subtracting v1 from v2 and drawing it that way, and you would get the same answer. And so let's look at this for a second. If we draw delta v halfway between the two positions, we get something that looks like this. This is our delta v here, right? And so you've probably experienced this in a car. If you're going around a curve in a car, you feel yourself pushed. Maybe you lean against the outer door or something like that, and it's pushing you towards the center. You're actually being accelerated towards the center. The acceleration is given by delta v over delta t, right? That's the definition of the acceleration. And so the direction of the acceleration is towards the center of the circle. And so we say this acceleration, we call it, we give it a sub c. We put a little c next to it, and we say it's the centripetal acceleration. Centripetal means center seeking. I've apparently reached the boundary of my screen there. But a centripetal acceleration always points towards the center. In fact, you could pick any 2 points. If you picked this point where the velocity is kind of going this way, and this point where the velocity is kind of going this way, the delta v would again point towards the center. And so you would always, no matter which points you picked going around the circle, have sort of the instantaneous delta v pointing towards the center of the circle. And that's the direction that acceleration points. It's just delta v whatever its magnitude and direction is, divided by the magnitude of the time difference. So now we're going to try to evaluate the magnitude of the centripetal acceleration. The centripetal acceleration a sub c is defined as the change in velocity over the change in time, and I'm going to try to give us a graphical argument that's going to get us its magnitude. Its direction is always going to be towards the center of the circle for the arguments I made in the last screen. But now we're going to look at what its magnitude is. And so I've drawn this object at position 1 at time t1 and position 2 at time t2, my little car or whatever it is that's going around the circle at a constant speed. Its velocity at t1 is horizontal here. It's represented by v1, and its velocity later is angled downward because it's further along around the circle. In fact, it's moved in angle theta around the circle. And these little orange lines here are the radius of the circle. And so we know that the radius is perpendicular to the velocity always because the object is moving in a circle. And that means the velocity is tangent to the circle. And that means that since the tangent is always perpendicular to the radius, that's the definition of the tangent, we know those the radii, the velocities and the radii are perpendicular. And so I can make a little statement over here. I can draw these some triangles. And so what I'll do is I'll grab my blue color here, and I'll, just like I did before, I'll draw my V. Here's my V1, right? And here's my V2, right? And here's my delta V between them, right? And similarly, I'm going to grab my orange pointer over here, my orange color, right? And I'm going to draw this triangle with that I have over here with my radii, right? Maybe that one's tipped just a little more like that, right? Try it again. I just want a straight line there, right? And then the top of that triangle is represented. I have a green line in the picture, but I'll just draw it this way, right? So each one of these is an R, and this angle is theta. And so in this picture, in the picture with the radii and the angle, I can say, look, the two radii are equal, right? This line and this line are equal since they're both radii, and they have an angle between them, theta. And I'm going to make the argument that, look, since the object is moving at constant speed, the two velocities are the same. That is to say, this velocity here and this velocity here, sorry, the speeds are the same, right? Because it's moving in a circle at constant speed. The velocities are not the same because the direction changes, but the speed does not change. And so this triangle up here has two equal sides separated by an angle theta, and this triangle down here has two equal sides separated by an angle theta. And that's side angle side. That means these two triangles are similar. So I can write similar triangles. And so that's a key point for determining the acceleration. And so on the next screen, we'll use the fact that these two triangles are similar to determine the centripetal acceleration. So we're going to continue determining the magnitude of the centripetal acceleration. And we can just write that as, see if I get it right here, delta V over delta t, right? We're looking for the magnitude of this thing. If I want to call the a sub c a vector, but I want its magnitude. And so what we've already learned is that we have these two triangles, one that's made by the velocity v1, v2, and the change in velocity, and the other one that's made by the two radii. The reason the angles between these two between the two velocities and the two radii are the same is because the v1 is just 90 degrees rotated from this r, and v2 is 90 degrees rotated from that r, and so the angle between those two comes out the same when you put them together. And so what that says is that these two triangles are similar. And what that means is that the ratio of corresponding sides of similar triangles is similar, And so if I want to just write the length of these sides just being the magnitudes of these vectors, I can say, look, the magnitude of the change in velocity, or delta v, divided by v is equal to delta s divided by r, right? That is the length of this side divided by a radius is equal to the length of this side divided by one of its sides, and these sides both have the same magnitude, which is just v. And so then I can take this equation, I can say, well, look, delta v then is equal to v times delta s over r. But the magnitude of the centripetal acceleration, that is a sub c, is just equal to delta v over delta t. That is where this is just the magnitude of the change in velocity vector, right? And so if I want the magnitude of a sub c, it's just delta v over delta t. What is that? That's equal to v over r, just whatever we had over here, times delta s, and I have to divide this side by delta t, and I'm going to put the delta t right there, right? And so this says the magnitude of the centripetal acceleration is equal to v over r times delta s over delta t, right? Delta s is this distance between these two radii. What is that really? That's just the distance that's traveled by the object. It's the straight line distance between the tips of these two radii. But as long as they're very close together, like infinitesimally small, then that's just an approximation to the arc length that follows the circle, right? And if they're infinitesimally small, it's equal to the arc length. And so this just becomes a sub c is v over r times delta s over delta t. But delta s over delta t is just the rate of motion of the object, which is just v. So it's v over r times v, or v squared, over r. And so the magnitude of the centripetal acceleration, I'm writing it this way without the vector line above it to indicate that I'm just talking about the magnitude, is v squared over r. And this is true for any object moving at constant speed in a circle. That's the definition of the magnitude of the centripetal acceleration. The direction of the centripetal acceleration is always towards the center of the circle. So to sum up, for centripetal acceleration, that is the acceleration of an object moving in a circle at a constant speed, the direction is towards the center of the circle. It's always inward. The magnitude is v squared divided by r, where v is the speed of the object and r is the radius of the circle it's moving in.